Good morning, all. Welcome to the lecture of measure and integration. Am I audible?
Yes, sir.
Yes, sir.
Okay, thank you.
Good morning, sir.
Good morning. Okay, so in last lecture we have seen what is the Radon Nikodym theorem. Radon Nikodym theorem is nothing but late. Its statement is nothing but Radon Nikodym theorem, and it states that let capital X curly b mu be a sigma finite major space of finite major space, and gamma be a major defined on curly b, which is absolutely continuous with respect to mu, absolutely continuous with respect to the measure mu. Then there is a non-negative measurable function, non-negative measurable function f, such that for each set e in curly b, that is each measurable set e, we have gamma of e is nothing but integration over set e of f d mu, and after that we have proved its uniqueness. Such a existence of such a function f will be unique. That is it. Further, if g is any other further if g is any other measurable function with this property with this property, then f equal to g almost everywhere with major mu. Okay, that is we have already seen in the last lecture, but we have seen its half a part. That is we have seen for the triplet x curly b mu is a finite major space. Now just we have to extend it to a sigma finite major space, and if we have proved it is also true on sigma finite major space, then we will get a proof for Radon Nikodym theorem. Okay, so in last lecture we have assumed that mu be a finite major space, and we have make gamma of e equal to integration over set e of f d mu, and after we have proved that the uniqueness for this, but there mu will be our finite major space. Today we will see it is also true for a sigma finite major space. Okay, so see Radon Nikodym theorem for sigma finite major space. Radon Nikodym theorem for sigma finite major space. Major space. Okay. Now let sorry let capital X curly b mu be a sigma finite major space. What is this mean by sigma finite major?
There is a sequence of measurable sets such that x equal to union of that sequence xn, and measure of xn is less than x.
Measure of xn will be finite for each value of n. So there exists a disjoint sequence of measurable sets, xn, whenever n running from xn, n running from 1 to infinity, such that our capital X is nothing but union over n running from 1 to infinity, this xn, and measure of xn is finite for all n, which is from the definition of sigma finite major. Since here we have taken this triplet capital X curly b mu be a sigma finite major space. Now let curly bn be a sigma algebra of sigma algebra of measurable subsets of Xn. Measurable subsets of Xn. Since here Xn, each Xn is measurable and having measure will be finite. Okay. So curly Bn be a sigma algebra of measurable subsets of Xn we have taken. Let us define this curly Bn as it is a set which contains all the elements E intersection Xn whenever E belonging to curly B. Okay, let us denote this E intersection Xn as a En whenever E is belonging to curly B, since En is nothing but E intersection Xn. Okay, now here measure mu is a sigma finite measure. As it is a sigma finite measure, then measure of Xn is finite for all n. Curly B and be a sigma algebra. Then we get one new triplet, capital X Xn, curly Bn and mu, which is a finite measure space. Is a finite measure space. Since any measure is said to be a finite measure if measure of whole universal set X will be finite. As here measure of each Xn is finite. Therefore, as we have considered this triplet, capital Xn, curly B and mu, and mu be a sigma finite measure space, but measure of, as mu is a sigma finite measure space, measure of Xn is finite for each value of n. Therefore, measure of Xn is finite. As measure of Xn is finite, and we take one triplet, this capital Xn, curly Bn and mu n. Curly Bn is already a sigma algebra. Xn is a finite measure space. Therefore, our triplet will be a finite measure space. But in last lecture, we have proved the Radon-Nikodym theorem is true for finite measure space. According to that theorem, there exists one non-negative measurable function. There exists a unique non-negative measurable. Since we have proved the uniqueness, unique non-negative measurable function small fn such that gamma of E is nothing but integration over set E of fn of d mu whenever E is belonging to curly B, which is from the Radon-Nikodym theorem for finite measure spaces. Okay, now let us define one function. Define a function small f on x by f of x is nothing but fn of x whenever x is belonging to xn. Okay, so here we have defined one function small f on capital X by f of x is nothing but fn of x whenever x is belonging to xn, but capital X is nothing but union over n running from 1 to infinity xn. Therefore, f of x, as this fn is a non-negative measurable, but fn of x is greater or equal by 0 for each value x belonging to this xn, and union over n running from 1 to infinity xn is nothing but capital X, and fnx is greater or equal by 0 for each value x belonging to xn. It means f of x is greater or equal by 0 for each value x is belonging to x, since x is nothing but union over n running from 1 to infinity xn, and each element small x belonging to xn, fn of x will be greater or equal by 0, and capital X is a union of this one, then it must be greater or equal by 0, which implies f is a non-negative measurable function. Non-negative measurable function on capital X. Okay, now take this one as a star. Consider gamma of E. Consider gamma of E, which is equal to gamma of E. As E is any subset, E is a measurable subset, then E must be a subset of X, since it is a member of curly B, and curly B contains all these measurable subsets of X. Therefore, E can be written as E intersection X, which is equal to gamma of E intersection. But X is nothing but union over n running from 1 to infinity xn. Put that value, union over n running from 1 to infinity capital xn. Okay, now there is no term of n in this E, therefore it can be written as gamma of union over n running from 1 to infinity E intersection xn. But we have gamma is a measure. As gamma is a measure, which implies summation n running from 1 to infinity gamma of E intersection xn. But in we find curly bn, E intersection xn is we have taken curly en. Therefore, it is nothing but summation n running from 1 to infinity gamma of en. Okay, so here we get gamma of en. But from start, gamma of E is nothing but integration over set E of fn of d mu whenever E belonging to curly b. As E is also a member of E is belonging to curly b, xn is also a measurable set. As it is measurable set, it must be belonging to curly b. Therefore, its intersection must be belonging to curly b. Therefore, each en is belonging to curly b. Okay, therefore it is also measurable. Then by this star summation en running from 1 to infinity, gamma of en is nothing but integration over set en of fn of d mu. Okay, now first here somewhere let us define capital E is nothing but union over n running from 1 to infinity en. After that we will consider gamma of E. Okay, so now as each en is a disjoint measurable set, then summation of integration over set en is nothing but integration of union over n running from 1 to infinity en, and which is nothing but fn of d mu. But fn is equal to f for each value x belonging to xn. Therefore, fn we can replace this fn by f. Okay, and union over n running from 1 to infinity en is nothing but our e. Therefore, e and it is fn of d mu. But as fn is nothing but f for each value x belonging to xn, and x is nothing but union over n running from 1 to infinity xn. Therefore, actually this fn is nothing but f. Therefore, here integration over set e of f d mu, since fn is equal to f. That is we have defined a function. Therefore, here we get gamma of e is nothing but integration over set e of fn, sorry, f of d mu, and that is we have to prove. And here our mu will be a sigma finite measure, and hence the required result. तुम्हाला काही डाऊट यामध्ये?
No, sir.
Okay. So here our Radon-Nikodym theorem will be completed. Since actually we have to prove the Radon-Nikodym theorem for sigma finite major space, and to prove it is true for sigma finite major space, we have first proved it is true for some finite major space, and after that we have extended it to a sigma finite major space, and it is also true for the sigma finite major space also. Okay, now there is one note. Depending on this theorem, let capital X curly b mu be a sigma finite major space, finite major space, and for every gamma absolutely continuous with respect to mu, there is a unique non-negative measurable function, non-negative measurable function f, measurable function small f, such that gamma of e will be equal to integration over set fn of, sorry, f of d mu. Set f of d mu for each e belonging to curly b. Okay, so that is, it is nothing but the Radon-Nikodym theorem. If you consider one sigma finite major space and gamma is a major which is absolutely continuous with respect to mu, then there exists one unique non-negative measurable function f such that gamma of e will be equal to integration over set e of f d mu for each e belonging to measurable set. This function f is called the function f is called the Radon-Nikodym theorem, sorry, Radon-Nikodym derivative, Radon-Nikodym derivative of gamma with respect to major mu. Okay, and it is denoted by F is equal to radon Nikodym derivative of gamma with respect to mu. Okay, just replace this value F in integration. We get gamma of E is equal to integration over the E of F is nothing but radon Nikodym derivative of gamma with respect to the measure mu of d mu. Okay, so according to Radon-Nikodym theorem, we get gamma of equal to integration over set E of F d mu. But this F is nothing but Radon-Nikodym derivative of gamma with respect to mu. That is, if we take d gamma by d mu, then we get on RHS we get F. Therefore, actually F is nothing but Radon-Nikodym derivative of gamma with respect to the measure mu, and it is denoted by this symbol. That is F equal to square bracket d gamma of d mu, which is and which can be read as it is a radon Nikodym derivative of gamma with respect to the measure mu. And from if we put F equal to radon derivative of gamma with respect to the measure mu, then this gamma of is nothing but integration over set E of the radon Nikodym derivative of gamma with respect to the measure mu. Okay, so now in radon Nikodym theorem we have taken the measure mu is a sigma finite measure. What should be happen if it is not a sigma finite measure? Let us see. We will do this one. Okay, now show that the condition of sigma finiteness is essential in the Radon-Nikodym theorem. Okay, so here we have to show that the sigma finiteness, the condition of sigma finiteness is essential in the Radon-Nikodym theorem. So here we will take one measure mu, which is not a sigma finite, and let us see what should be happen. Okay, so it's a solution. Let us take, as we have to take capital X curly b mu be a major space, then we will take capital X as closed interval 0 1 curly b be a sigma algebra of measurable subsets of X, measurable subsets of capital X, and mu is a counting measure. Counting measure means that is measure of equal to the number of elements in E. Such a measure is called counting measure. Number of elements in E. Okay. Now, so here we have taken capital X curly b mu be a major space in which capital X is nothing but closed interval 0 1 curly b be a sigma algebra of all the measurable subsets of X, and curly mu is nothing but the counting measure. It means measure of E. Suppose we have considered measure of E, then measure of E is nothing but the number of elements in capital E. Okay. So now, if we take, so measure of E will be equal to 0. Measure of E equal to 0, and as measure is a counting measure, mu is a counting measure, that is number of elements in E, then when it is possible that measure of E will be equal to 0?
If E is empty set.
If E is empty set, then only it is possible that measure of E will be equal to 0. Therefore, as we have taken measure of E equal to 0, then E must be equal to 5. Okay, so as E equal to 5 and gamma, let us consider here we have to take gamma is one another measure. Okay, let gamma be a Liebig measurable. Liebig measure. Liebig measure. As we have taken gamma be a Liebig measure, then what is the gamma of phi? Gamma of phi is also 0 since already it is measure. So if we take measure of any set E will be equal to 0, as mu is a counting measure, then it is must be equal to phi. As E equal to phi and gamma is one another measure, then it must be gamma of phi will be equal to 0. So if we take measure of E equal to 0, then gamma of E must be equal to 0. Then by the definition of absolutely continuous measure, two measures gamma and mu are said to be absolutely continuous. That is, the measure gamma is said to be absolutely continuous with respect to the measure mu. Whenever measure of E will be equal to 0 for any E belonging to curly B, then gamma of E is also equal to 0. So here we have taken measure of E equal to 0, and which implies that E equal to phi. And whenever E equal to phi, then gamma of phi must be equal to 0. That is gamma of E equal to 0. So if we take measure of E equal to 0, then we get gamma of E equal to 0, which implies gamma is absolutely continuous with respect to mu, which is from the definition of absolutely continuous measure. Absolutely continuous measure. Now here clearly our measure mu is not a sigma finite measure since capital X will be equal to closed interval 0, 1. So it is not possible that it can be written as a countable union of disjoint measurable sets such that capital X equal to union over interval from 1 to infinity xn, and measure of xn will be equal to finite. We can write this capital S as the union of some open intervals, but here measure mu is a counting measure. It means it contains the it is nothing but the number of elements in that set. If we write any this closed interval 0, 1 as a union of open intervals, then each open interval contains uncountable number of elements. Therefore our measure is not defined since measure of E will be equal to number of elements in, and if it contains the uncountable number of elements, then measure of that open interval will be equal to finite depending on the definition of counting measure. So here it is not possible that capital X will be equal to union over n running from 1 to infinity xn, and measure of xn is finite for each value of n. Therefore here mu is not a sigma finite measure. So clearly mu is not a sigma finite measure. हे कळते का? क्लोज्ड इंटरवल 0, 1 आहे माझ्याकडे x हा. मी त्याला लिहू शकतो मध्ये त्या क्लोज इंटरवलला जरी लिहिला तरी माझा मेजर म्यू काय दिलाय, काउंटिंग मेजर दिलाय. काउंटिंग मेजर म्हणजे असा मेजर आहे जो की त्यामध्ये किती एलिमेंट आहेत हे सांगणार आहे. जर मी ओपन इंटरवलच्या युनियन मध्ये लिहिला तर प्रत्येक ओपन इंटरवल मध्ये माझ्याकडे अनकाउंटेबल नंबर ऑफ एलिमेंट्स असतील. मग प्रत्येक ओपन इंटरवलचं मेजर काय होईल, माझा इन्फायनाइट होईल, कारण दिलेलं मेजर हा काउंटिंग मेजर आहे. सो असं इथं पॉसिबल होणार नाही की कॅपिटल एक्स हा युनियन मध्ये येईल काहीतरी मेजरेबल सबसेटच्या आणि त्याचा मेजर प्रत्येक वेळेला फायनाइट येईल, कारण इथं माझा मेजर तर इन्फायनाइट येईल. याच्यावर म्हणू शकतो का म्यू हा सिग्मा फायनाइट मेजर नाहीये म्हणून?
Yes, sir.
Okay, so here clearly mu will be not a sigma finite measure. Okay, now if possible, suppose that there exists a non-negative measurable function f. There exists a unique non-negative measurable function f such that gamma of E is equal to integration over set E of f dv whenever E is belonging to curly B. Okay, now let each x belonging to x, that is equal to each singleton x, is a measurable set. Since we know that singleton sets are always measurable, is a measurable set, that is singleton x are belonging to curly B. Okay, now as each singleton set is a measurable set, what is the measure of singleton set? Measure of
Zero.
singleton set which is equal to
0.
0. Therefore, as here we have taken equal to singleton set, and singleton sets are always measurable, and having measure will be equal to 0. So gamma of E is equal to 0. So but gamma of E is nothing but integration over set E of F dv. Okay, but here we get gamma of E will be equal to 0, which implies integration over set E of F d mu will be equal to 0. That is integration over set E of F d mu is equal to 0. Again, there is one theorem. If integration over set E of F d mu will be equal to 0, then F must be equal to 0 almost everywhere, which implies F equal to 0 almost everywhere with respect to the measure mu. Okay. Now, here we get F equal to 0 almost everywhere. It implies F equal, there is no F is not equal to 0 if we collect all those points and find out equal to 0, which implies by the definition of almost everywhere, if we take all the points x such that F of x is not equal to 0, then its measure will be equal to 0, which is from the definition of almost everywhere property. But here measure mu is a counting measure. If measure of this set will be equal to 0, then what is this set?
Empty.
मेजर मी हा काउंटिंग मेजर घेतो, परत हा सेट माझा एम्प्टी होईल, विच इम्प्लाइज दिस सेट एक्स व्हेनेवर एफ ऑफ एक्स नॉट इक्वल टू 0 हा माझा एम्प्टी सेट येईल. म्हणजे यामध्ये मला एकही एलिमेंट मिळणार नाही. याचा अर्थ असं म्हणू शकतो का, विच इम्प्लाइज एफ ऑफ एक्स is equal to 0 for each value x is belonging to capital X. Okay, so which is nothing but f equal to 0 on x. If f equal to 0 on x, then integration over set x of f d mu will be equal to 0, since f equal to 0 on x, that is for each value x belonging to x, f is equal to 0, then integration over set x of f d mu must be equal to 0. Now here we get integration over set x of f d mu will be equal to 0. Now gamma of x consider, but capital X is nothing but closed interval 0 1, which is nothing but closed interval 0 1. Now what is the measure of closed interval 0 1?
1.
Which is equal to 1. So here we get gamma of x equal to 1, and integration over set x of f d mu will be equal to 0. Since here we have proved that gamma of E is nothing but integration over set E of f d mu. That is, if gamma of x is equal to integration over set f of d mu. Since it is true for any measurable set E, and closed interval 0 1 is also a measurable set, then gamma of equal to integration over set x of f d mu. हे माझं आलं पाहिजे, पण हे येते का माझं? Gamma of x is nothing but 1, and integration over set x of f d mu is nothing but 0. Whether it is possible that 0 equal to 1? असं शक्य आहे का?
No, sir.
No.
So this
No,
will be
sir.
contradict to our supposition. Which supposition? Here exists one non-negative measurable function f such that gamma of p equal to integration over set e of f d mu whenever mu is not a sigma finite measure, which implies there does not exist a non-negative measurable function f, non-negative measurable function f such that gamma of e is equal to integration over set e of f d mu. ओके, सो इथं बाकीच्या गोष्टी सर्व तर आपण सेमच घेतल्या होत्या, जसं की रेडॉन निकोडिम थेरम मध्ये घेतलं होतं. फक्त एकच गोष्ट वेगळी होती ते की दिलेला मेजर म्यू हा सिग्मा फायनाइट मेजर होता. सो इफ वी टेक मेजर म्यू विच इज नॉट अ सिग्मा फायनाइट मेजर, देन वी get this property, that is this contradiction, gamma of x is not equal to integration over set x of f d mu. Therefore from this we conclude that the condition of sigma finiteness is essential in the Radon-Nikodym theorem. Okay, so which implies the condition of sigma finiteness is essential in the Radon-Nikodym theorem. And here the required our result. Okay. So now any doubt?
No, sir.
Oh, there is no doubt. Now let gamma 1 is absolutely continuous with respect to mu and gamma 2 is absolutely continuous with respect to mu. Then prove that then prove that radon Nikodym derivative of gamma 1 plus gamma 2, which is denoted by this symbol, radon Nikodym derivative of gamma 1 plus gamma 2 with respect to the measure mu is nothing but radon Nikodym derivative of gamma 1 with respect to mu plus radon Nikodym derivative of gamma 2 with respect to mu. Okay, so here we have given that gamma 1, gamma 2 and mu are three measures, and we have to and such that gamma 1 is absolutely continuous with respect to mu and gamma 2 is absolutely continuous with respect to mu, and from that we have to prove that the radon Nikodym derivative of gamma 1 plus gamma 2 with respect to the measure mu is nothing but radon Nikodym derivative of gamma 1 with respect to measure mu plus radon Nikodym derivative of gamma 2 with respect to the measure mu. Okay, now seeds prove given that gamma 1 is absolutely continuous with respect to, actually this example is or this theorem is depending on the radon Nikodym theorem. Okay, so here measure mu is already our sigma finite measure under consideration. Okay, so as we have gamma 1 is absolutely continuous with respect to mu, then by the statement of radon Nikodym theorem, as we have one gamma 1 which is absolutely continuous with respect to mu, then then there exists a unique non-negative measurable function f1, non-negative measurable function f1 such that gamma 1 of e is equal to integration over set e of f1 of d mu. Take this one as equation 1, and which is from the radon Nikodym theorem. Now similarly we have and gamma 2 is absolutely continuous with respect to mu, which implies again there exists a non-negative measurable function, negative measurable function small f2 such that gamma 2 of e is equal to integration over set e of f2 of d mu. Take this one as equation 2. Okay, which is from given as gamma 1 is absolutely continuous with respect to mu, then there exists one unique non-negative measurable function f1 such that gamma 1 of e is nothing but integration over set e of f1 d mu, and similarly as gamma 2 is absolutely continuous with respect to mu, then there exists one another non-negative measurable function f2 such that gamma 2 of e is nothing but integration over set e of f2 d mu. But as here we have gamma 1 and gamma 2 are two measures, then gamma 1 plus gamma 2 must be a measure. Okay, so as gamma 1 and gamma 2 are measures, then gamma 1 plus gamma 2 is again a measure. Is again a measure. Okay, and we know that if gamma 1 is absolutely continuous with respect to mu and gamma 2 is absolutely continuous with respect to mu. Okay, so in after the definition of absolutely continuous measure, we have defined if gamma 1 and gamma 2 and mu are three measures in such that gamma 1 is absolutely continuous with respect to mu and gamma 2 is absolutely continuous with respect to mu, to mu. Then its any linear combination is again continuously absolutely continuous with respect to mu. That is C1 gamma 1 plus C2 gamma 2 is absolutely continuous with respect to mu. We have proved this one. Similarly, the C1 gamma 1 plus C2 gamma 2 is mutually similar with mu. If gamma 1 is mutually similar with mu and gamma 2 is mutually similar with mu. Therefore, from this result, if as gamma 1 is absolutely continuous with respect to mu and gamma 2 is absolutely continuous with respect to mu, then gamma 1 plus gamma 2 must be absolutely continuous with respect to mu. Therefore, here one we get one more measure gamma 1 plus gamma 2 which is absolutely continuous with respect to mu. Then again by the definition of by the statement of Radon-Nikodym theorem, which implies there exists a non-negative measurable function here, non-negative measurable function small f such that gamma 1 plus gamma 2 of E is nothing but integration over set E of f of d mu for any measurable set E. Okay, so as gamma 1 plus gamma 2 is absolutely continuous with respect to me, then gamma 1 plus gamma 2 of E is nothing but integration over set E of f d mu. Now let us consider gamma 1 plus gamma 2 of E, and we know that measure is a holds the linearity property, which is nothing but gamma 1 of E plus gamma 2 of E. But from equation 1 and 2, gamma 1 of E and gamma 2 of E are nothing but integration over set E of f1 of d mu plus integration over set E of f2 of d mu. As integration is closed under the linearity property, therefore it is nothing but integration over set E of f1 plus f2 of d mu. Okay. Now, comparing equation 3 and 4, we know that Radon-Nikodym theorem holds the uniqueness property also. That is, if f is a any non-negative measurable function such that gamma of p equal to integration over set E of f d mu, then it holds the uniqueness. Since if g is any other measurable function with this property, then f and g must be same with respect to the measure mu. So as here, gamma 1 plus gamma 2 of E equal to integration over set E of f d mu, and gamma 1 plus gamma 2 of E is nothing but the integration over set E of f1 plus f2 of d mu. Then by uniqueness we get by uniqueness we get f is equal to f1 plus f2. Okay, now as f is equal to f1 plus f2, take this one as equation 5. Now from equation third, the gamma 1 plus gamma 2 of E is nothing but integration over set E of f d mu. After Radon-Nikodym theorem, we have defined one note, that is if capital X curly b mu be a sigma finite major space and a gamma is absolutely continuous with respect to mu, then there exists a non-negative measurable function f such that gamma of E equal to integration over set E of f d mu, and the function f is called the Radon-Nikodym derivative of gamma with respect to the measure mu. As here we get gamma 1 plus gamma 2 of E equal to integration over set E of f d mu, that is from equation 3. Then here function f is nothing but the Radon-Nikodym derivative of gamma 1 plus gamma 2 with respect to the measure mu. Therefore, from 3, f is nothing but Radon-Nikodym derivative of gamma 1 plus gamma 2 with respect to the measure mu. Okay. Similarly, from equation 1 and equation 2, Radon-Nikodym derivative, sorry, f1 is nothing but Radon-Nikodym derivative of gamma 1 with respect to the measure mu, and f2 is nothing but Radon-Nikodym derivative of gamma 2 with respect to the measure mu. So here we get the values of f, f1 and f2. Just put out the values of f, f1 and f2 in equation 5. Then we get, which implies Radon-Nikodym derivative of gamma 1 plus gamma 2 with respect to measure mu is nothing but Radon-Nikodym derivative of gamma 1 with measure mu plus Radon-Nikodym derivative of gamma 2 with measure mu. Okay, so which is the required result, hence the proof. Okay, any doubt?
No, sir.
Okay. Now there is one note. First, if suppose gamma is absolutely continuous with respect to mu and mu is absolutely continuous with respect to lambda, then radon Nikodym derivative of gamma with respect to lambda it can be written as radon Nikodym derivative of gamma with respect to major mu plus radon Nikodym derivative of major mu with respect to the major lambda. Okay, which is just our as our partial derivative. Okay, as gamma is absolutely continuous with respect to mu and mu is absolutely continuous with respect to lambda, then radon Nikodym derivative of gamma with respect to lambda is nothing but radon Nikodym derivative of gamma with respect to mu plus radon Nikodym derivative of mu with respect to lambda. And second note is, if gamma is absolutely continuous with respect to mu and mu is absolutely continuous with respect to gamma, then radon Nikodym derivative of gamma with respect to the major mu is nothing but radon Nikodym derivative of mu with respect to gamma, its inverse. Okay, so radon Nikodym derivative of gamma with respect to the major mu is nothing but the radon Nikodym derivative of major mu with respect to gamma and its inverse. Okay,